So Mike gave a very good introduction of myself. I know relatively little about the geology of Warwickshire. I'll hold my hands up. Although I am originally from the Cotswolds, I'm from Stow-on-the-Wold. So I know the oolite, the Jurassic limestones, extremely well, and I guess some of those go across up into Broadway and up into Warwickshire as well. So without further ado, let me attempt to share my screen. Let's see how this goes. Can you all see that? That should be a PowerPoint presentation. Is that, can you see my PowerPoint?
Yes, it's clear.
Jolly good. It's nice to hear some feedback when when one speaks to undergraduates on Zoom, you expect silence when you're doing it virtually. So it's nice to hear some feedback. So I thought today we would speak about some research that I have been doing for the past, well, 10 years really, at Imperial, Cambridge, and now at Royal Holloway, University of London, into the geology of London and the way it affects the course of major engineering projects such as Crossrail, Thames Tideway, and the London Underground and extensions. So the talk will be roughly split into two parts. The first part will be a sort of broad background into the geology and the structure of the London Basin, including the way in which the tube was constructed and various construction calamities that befell the tube when it was being constructed in Victorian times. And then the second part will deal more explicitly with the chalk aquifer, which is Britain's most important aquifer underneath London, with respect to London's water resources. And I put a couple of slides at the very end, which will discuss some very new research, which I got funding for last week, as it happened, which is to do with cooling down the tube network, cooling down the London Underground network using groundwater and buried river water. So we'll discuss that right at the very end in about an hour. Okay, so before we begin, this is from a paper I published 4 years ago. I think it's instructive to consider what one means when you speak about London. So there are 4 pictures here with this bold black outline showing the outline of Greater London as defined by the census area. And then we've got 4 different ways of conceptualizing London. So in the top left, we've got the kind of geological way of thinking about London, where the dashed line shows the boundaries of the outcrop of the chalk. We've got the Chilterns up here, and then the North Downs down here. And then the grey lines are an elevate. The grey shading is an elevation contour. So I think this is all land above 50 meters is shaded in grey. So you can see this kind of approximates Greater London reasonably well. You can see the London Basin striking northeast, southwest like this. There are various other ways in which London can be defined. So if you consider the London postcode area and the 020 dialing area, these approximate Greater London reasonably well. Ditto the Oyster Card area, the TfL railway station area and the buses, they do a fairly good job. And then also down here we've got the M25, the inner circular, and the contiguous urban area. So this was just to illustrate, before we go into the geology, the fact that London is very poorly defined, much like Birmingham, much like arguably Leamington, Warwick, anywhere like that. You know, it's very subjective. It's a matter of subjectivity. So my contention is that the landscape is one of the best indicators for delineating London. So on the left-hand panel here, this is a digital elevation model, so topography, showing the Greater London region. So we've got the Chilterns up here, white is high elevation, and then we've got the North Downs, the green sand, and then the Weald down here. So if you have a look at Greater London superimposed upon the topography, you could try and imagine London as kind of washing up, the houses washing up against the Chilterns over here and against the North Downs down here in Croydon and in Bromley. So arguably topography, which is governed by geology, is one of the best indicators as to the formation of Greater London, you know, its extent, how far it's reached. Okay, so this is a figure from one of the BGS guides about 25 years ago, which shows the geology of London. And you can see the London Basin striking northeast, southwest. So this is the axis of the syncline going straight through the centre of London, straight through Westminster, Chertsey, etc. And what I'll do now is I will show a cross section from the northwest up here towards Luton down towards the southeast, Croydon. So what you can see is that the stratigraphy of the London Basin is folded in a highly asymmetrical manner. So all of the stratigraphy was folded in the Alpine orogeny, so about 25 million years ago. And you can see the basin is highly asymmetrical. So we've got London clay here in grey, chalk here in light green, and then all of the lower Jurassic, or the lower Cretaceous rather, beneath it in these greens and blues beneath it. So the highest points in London are formed of the London clay. We've got Hampstead Heath up here, and then Crystal Palace in the south, and they're formed of a particular formation or a member within the London clay called the Claygate member, which is a particularly resistant band of clay within the London clay. And if you look beneath central London, most of the tunnels, the kind of engineering tunnels, the tube tunnels, the water tunnels, etc., are about 10 to 20 meters beneath the surface. And then the very deepest tunnel, Thames Tideway and Crossrail, are maybe 50 meters beneath the surface, so just about getting into the chalk. The way in which the aquifer recharges, you have rainfall falling on the North Downs in Croydon and beyond, and then the Chilterns, which then slowly percolates down over hundreds of years to collect beneath central London. And this is one of Britain's major water sources. Just a side note before we move on, I think Jim Rose from Holloway, from my institution, may have spoken to you at some point. The River Thames has not always been in the same position. Based on the provenance of gravels and river terrace deposits, we know that over the past 500,000 years, the River Thames has moved southwards. So 500,000 years ago, the course of the River Thames would have been somewhat farther northwards compared to nowadays. So it would have flown through St Albans, Bishop Stortford, and it would have exited England somewhere near Ipswich. This was just a sort of just a side note. Okay, so the way I'm going to do this, the talk, we're going to go progressively down the stratigraphy, starting from Eocene time, so about 50 million years ago with the London clay, which of course London is extremely famous. And then we're going to look at the stuff below it, the sands of the lower London tertiaries, and then we're going to finish up with the chalk, will be the second part of the talk. So the London clay is extremely stiff, highly impermeable, being clay, and it has good load-bearing characteristics, which means when you drill tunnels through it, the tunnels won't subside, they won't uplift, they'll generally stay in the same place. And this is one of the main reasons why the tube developed when it did, before the metro in New York, before the Metropolitan in Paris. It developed a long time ahead of these because of the geology. You can see that it varies quite considerably across central London, with the greatest thicknesses in the west. And as soon as you get to Canary Wharf and the Isle of Dogs, the London clay disappears altogether. And it's a similar thing when you go south of the river, which is one of the reasons given why there are so few tube lines on the wrong side of the river. Of course, there are many competing reasons, such as the proliferation of overground railways south of the river. But one of the main reasons why you've got most tube lines in the north is geological. Okay, so the London clay, fantastic for building subterranean tunnels. If you go a little bit older to these, this is a deprecated name, the Lower London Tertiaries. They're now mostly known by the predominating formation of the Reading and Woolwich formations. These are not so good for drilling tunnels because they're mostly sands and gravels which become full of water when you are drilling through them. So it's ideally not ideal to drill through them because various engineering calamities could be created, such as you strike a sand lens which is full of water, which then might flood, and then you have various problems with people, workers on the underground who are going to suffer from the water. Okay, so historically, when drilling has taken place under central London, engineers have striven to avoid the London tertiaries or the Lambeth group here. Okay, so there are various problems encountered when over the past 150 years, engineers have been drilling underneath London, and they're mostly to do with gravel and water. So one of the most important problems is to do with this feature called the Scour Hollow. And the greatest concentration of these features is located here in Battersea, underneath Battersea Power Station. Of course, now the location of the Northern Line extension, which is actually going to open next week. So I'm definitely going to be travelling along the Northern Line next week. So these are things which they were developed in Devensian times, so during the last ice age. And essentially, they are large voids which formed following the thawing of large plugs of ice. After these plugs of ice thawed, they melted, they became filled with gravels, which were full of water. And they're very, very difficult to predict, even using relatively modern geophysical methods like ground penetrating radar. So these have only very recently been mapped, incredibly, only over the last 20 years. Another feature in central London, which is remarkably hasn't been mapped in great detail, the buried rivers. So these are rivers just like any other basin, any other catchment, which drain into the River Thames, but they've since become filled or overlain rather with concrete. So I'll show you a map in perhaps the next few slides, which shows you the distribution of these rivers. Okay, another major problem that was encountered when the tube was being built is this phenomenon of aggressive groundwater. So this is groundwater that's contained within the London tertiaries or the Lambeth group, which is combined with pyrite within the sand to form sulfuric acid. So this is extremely acidic groundwater which tends to rot the tunnel linings. And one place where this kind of rotting of the tunnel linings has been noted is over here. This is a very old photo I took maybe 10 years ago at Old Street on the Northern Line, where just north of this tunnel over here, the entire section of the tube had to be shut for 2 weeks, and they had to replace the tunnel lining because the acid had seeped through and was dripping down onto the tracks. So this is kind of pH 3 or pH 4, and it can actually dissolve concrete. So this was not ideal, and it was decided that the tunnel lining needed to be replaced. Okay, so the key point is that there are various problems, but one needs problems in order to originate solutions. So there have been various different tunneling methods that have been developed in response to specific geological conditions. So on the Victoria line, it was in the 60s and 70s, there was the hydraulic operation of a drum digger was developed. The Jubilee line extension, the drilling using drilling mud or bentonite was developed in the 90s. And then most recently of all, there was a technique called an earth pressure balance, which was developed when the Eurostar tunnels were being drilled underneath North London in the past 15 years or so. And increasingly, various different geological media besides the London clay can be drilled through, which wasn't considered possible over the last 20 or 30 years. Okay, and these are just some techniques which have evolved over the past 50 years or so. So various stations across the network, techniques like ground freezing, grouting, the use of compressed air, and the removal of water from gravel have been pioneered over the past 20 years in order to propagate the development of the underground. In the same way, there have been various different changes in the tunnel lining. So originally, this is Baker Street here, it was all brick, after which the most recent tunnel lining is part of the Jubilee Line extension in Southwark. This is bolted steel, which was shown to be effective against strata, which contained a lot of water. Okay, so one interesting case study is, from an engineering point of view, is the southern part of the Northern Line. If you look at it on the map, very straight line going straight down to Morden, the southern end of the Northern Line. If you look at it geographically, there is this ginormous bend from Collier's Wood to Wimbledon to Morden, so it doesn't go straight down at all. And the reason for this bend is purely geological. This blob here, just south of South Wimbledon, represents the headwaters of the River Wandle. So there are many lenses of sand down here which contain lots of water. So when the engineers were building this line in the early 1900s, rather than going straight through, they lacked the technology. So instead they diverted 90 degrees in order to avoid the water-filled strata and get back down to Morden. So this is one example of something that could be alleviated nowadays using modern engineering methods. Okay, so just very quickly, just have a look at some work that I've done which interrogates the way in which geology has affected the tunnel position laterally and vertically across the London Underground. So a couple of figures here which shows the Victoria line going north to south from King's Cross to Vauxhall, and the central line going west to east from Notting Hill all the way over to Liverpool Street. So what you can see, this is the stratigraphy down here with the London clay in grey, the chalk in green, and then the superficial deposits over here in yellow. You can see that where the London clay is very thick, the tube tunnels tend to go across the top of it. And then when it thins out, the engineers generally drill the tunnels close towards the bottom. There are various features that you can see in the stratigraphy, such as the centre of the London Basin, somewhere between Green Park and Victoria, this big thickness of London clay here. And then you can see a kind of anticline in the chalk here, which approximates the strike of Oxford Street. You can see here the anticlines bulge, kind of approximates Oxford Circus. And this is one of the reasons why Oxford Street developed in the first place, is because the ground was less boggy, because you're on top of an anticline, the clay is less thick and there's less water. Okay, so we can discuss this later if necessary. I also looked at the position of tube stations relative to the stratigraphy. So this shows the stations across central London, coloured. Each one is coloured by the platform level in absolute position above ordnance datum level. And then the grey filigree in the background is the base of the London clay. So you can see that there is a finger of very, very thick London clay which goes across kind of northeast to southwest London, which approximates the strike of the London Basin. Perhaps a more conceptually easy way of thinking about this is to reduce everything to showing the level of each tube platform above the base of the London clay. So what this means, I've coloured each of the tube stations by its position above the base of the London clay, so it's relative to stratigraphy. Basically, what this is showing is that the darker each of the tube stations are coloured, the deeper in the London clay they are. And when each of the tube stations is coloured red, this means they are located above the London clay, so they're in the sand of the Lambeth group. So again, what this shows is that we've got a finger of very deep London clay which goes approximately northeast southwest like this, mirroring the strike of the London Basin. And then these stations up here in red aren't in the London clay, they're all in the sand above the London clay, so they've all had to have various different engineering measures applied to them in order to maintain stability. So here we have Angel, King's Cross, Old Street. None of these are in the clay, they're all above it because the London clay is absent up here. Okay, so we're approaching the end of the first half. As a summary, geology is arguably the main constraint on how, where and when tunnelling has taken place for the London Underground over the past 150 years. And also any problems encountered largely spur solutions, engineering solutions, which are novel and which have been exported to various other countries in America and Europe, India, China, various other countries. In terms of the most important aspect of London's geology on tunnelling, there is some debate. So it's been argued that the continuity of the strata is the most important aspect with respect to tunnelling. Also, the strength of the clay, or even its presence, has been argued to be the most important aspect with regard to tunnelling. What my contention is that the permeability and the ability to harness water is the most important aspect of the engineering geology underneath London, and this links very nicely into the next part, which is the water resources of London, which we'll see in a minute. So you may have been following in the news Crossrail and HS2. I guess HS2 probably goes through Warwickshire. It's probably caused you some grief. You've probably been thinking about it quite a lot, but in London we've been thinking quite a lot about Crossrail and Crossrail 2. So this map here shows the progress of the second part of Crossrail from a vantage point of 2009. So this map is taken from 12 years ago, and it shows what the planners were thinking would happen back in 2009. So in 2009, it was suggested that Crossrail would be completed in 2019, and we would have this second part of Crossrail completed in 2022. And indeed, there will be other major engineering projects like an extension of the Bakerloo line southeast, which will be completed this year. So this clearly did not happen because of COVID, because of Brexit, because of various other things. So nowadays, what actually has happened, Crossrail will be completed as soon as possible. Who knows when that will be. The second part of Crossrail has been shelved as part of the Transport for London Rescue package last year, and any further extensions southeast have been permanently put on ice. So that was just to illustrate how the transport game in London is highly contingent on circumstances, and things can change at relatively short notice. Okay, so should we move on? We'll now move on to the second part of the talk, which goes down the stratigraphy and deals with the chalk, which hosts London's water resources and one of the most important aquifers in the United Kingdom. Okay, so we've dealt with the clay, we've dealt with the Lambeth group and the messy sands of the Lower London tertiaries, and now we've gone down from the Eocene down into the Cretaceous, and we'll have a little bit of the chalk. Okay, so most of southern England, just to refresh your memories, between 65 and 100 million years ago, looks something like this. So we've got ammonites, we've got various beasties, and we've got the incredibly rapid sedimentation of various milky coccoliths, which are collecting at unprecedented rates on the sea floor to form some of the greatest outcrops of any sedimentary rock anywhere in the world. So the chalk is an extremely exciting outcrop, and Britain is one of the best places to look at it. So there are relatively few outcrops that aren't at the coast, like the White Cliffs of Dover or the Seven Sisters. for geologists in order to collect samples. So one of the best places in London is relatively close to where I'm speaking to you from, in Croydon. So this is an example of a chalk outcrop. I'll flash on some interpretation. So the height is about 40 meters here, and this outcrop showcases three different formations. So this is the upper chalk, this is the top of the chalk, so about 65, 80 million years ago. Got the Seaford chalk, the Lewis chalk, and the lower Lewis chalk down here. I'm afraid this is a rather poor resolution photo taken from my very old phone camera, but perhaps you can make out there are some very nice flint marker horizons which can be traced across all of Northern Europe. And there are various hard grounds and other features of the chalk which have attracted a lot of international study. One of those marker horizons, this band down here, known as the Creel flints. I'll show a close-up here. So just for scale, this flint horizon here is about 1 inch thick. So this is a meaty sandwich of flint, likely formed due to the dissolution of silica-bearing marine animals. This is just one example of what the chalk looks close up. Okay, so that's fine. We've seen the chalk, but what bearing has it had on the development of the water resources in London? So I'm sure many of you have been to London and you've seen how it's perhaps not as busy now as it once was, but it's still quite busy. What about what happened if you go back 300 years? What does it look like? Well, London contained many rivers which have since been culverted or concreted over. The most prominent of this, or one of the most prominent, is the Fleet River, which goes up here, and this is a painting from 1750 which shows the River Thames in the foreground, and then the River Fleet coming up here, going towards the north, going towards Hampstead Heath. If you take a contemporary picture, looking towards the west, this is what remains nowadays. So you've got a little valley here, fairly small valley, whose contours have been infilled with made ground and concrete over the past 200 years. So this is Fleet Street going along here, and I'm standing next to City Thameslink railway station here, and St Paul's is behind me. If I flash on some interpretation, I mean, you can probably appreciate the valley is here. There's some topography. The River Fleet flows from up here, which is towards the north, towards Hampstead Heath, down towards the River Thames, towards the left. And I'm currently standing on some 60,000-year-old river terrace gravels known as the Kempton Park Gravel Formation. So most of central London nowadays, forget the London clay, forget the chalk, forget the low London tertiaries, most of what one would encounter are the gravels of the River Thames. And the Strand is one very good example of kind of a gravel terrace. Okay, so as promised at the beginning of the talk, here is a map of all of the lost or buried or subterranean rivers underneath central London. So the Thames in the centre winding its way through, and then all of these dotted green, dotted blue lines are the rivers which have been concreted over. We were just stood about here, on, looking over the River Fleet near St Paul's, but there are various other rivers, in particular the River Tyburn, which flows across Mayfair and then Westminster, and then actually splits in two underneath Buckingham Palace. So historically, before everything was concreted over, there actually used to be a major delta underneath Buckingham Palace, underneath Westminster Abbey, and what it would become the Houses of Parliament. So what is quite incredible is that this map has only recently been generated using modern geophysical methods over the past 20 years, because remarkably, nobody really knew where these rivers were to a degree of high precision until we had techniques like ground penetrating radar, seismic reflection, which only came along over the past 20-25 years. Okay, so if we look at an example of where some of these rivers are, we go back here and look at this River Westbourne, which flows into the River Thames through Hyde Park. The River Westbourne actually flows through the Serpentine. The Serpentine Lake isn't a lake, it's actually a very slow flowing river, which flows from up here near Paddington railway station down towards the south towards Sloane Square station and the Thames. And indeed, it's been culverted through various enterprising businesses, such as this antique store in Mayfair. This is the river, which actually flows underground through this antique store, and you can go here and see the river water being hosted to this these koi carp here. At Sloane Square, the river water flows from north to south, from right to left in this picture, across this ginormous green pipe, across the district and Circle Line platforms towards the River Thames. And if you're ever at Sloane Square station, you can stand underneath this ginormous pipe and listen to the river water gushing its way from Hampstead Heath down towards the River Thames. And there are various remnants of these rivers across central London. So two examples you can see here in North London in Farringdon and in Marylebone. You can see amongst the grid pattern there are two rather irregularly shaped streets. There's one here called Farringdon Lane, Terminal Street, and then in Marylebone there's a very historical lane, Marylebone Lane here. And if I flash on where the rivers are underneath the street pattern, you can see that the rivers are actually located immediately underneath these rather irregularly shaped streets. So these streets are extremely historical streets, which originally in medieval times would have been following the banks of these rivers. And then the kind of checkerboard street pattern, which grew up in Georgian times, would have kind of superimposed on top of this. And then you can see here there's some telltale names like Brook Street, which refers to the River Tyburn. Various other telltale signs of rivers in London. We've got Stamford Bridge, Chelsea's Ground, which was a bridge over a river. Knightsbridge, ditto. Holborn, Holborn is an old form of saying a river. Fleet Street, obviously. Deptford is the River Depp. Peckham, the River Peck. Wandsworth, the River Wandle, and Chelsea refers to the fact that chalk used to be landed on the northern embankment here from where it was extracted in Kent and Essex, chel being the Latin form for chalk. So there's a lot of geology encased in London street names. You just have to know where to look. Okay, so a little bit of history now about London's water resources. Some of you probably may have heard of Joseph Basil Jett, who developed the Victorian embankment and helped save London from the Thames being essentially a river which contained huge amounts of sewage. So in mid-Victorian times, the River Thames was getting in a very bad way, as evidenced by this cartoon from Punch during a period called the Great Stink. And so the Victorians, of course, were great improvers, and indeed they did improve Great London with a series of drinking water fountains under the auspices of this group called the Metropolitan Drinking Fountain and Cattle Trough Association. And if you go across London, you will see many of these fountains, which are incidentally generally gilded in some very beautiful rocks. So this is some form of granite, I guess, maybe a Shap granite. And there are various guides to these drinking fountains, which one can see from a sort of pavement geology point of view. One of the most important things the Victorians did to alleviate the problems of sewage in central London was to establish a series of pumping stations which discharged the sewage to the ebb tide of the River Thames, from which ideally it was intended that the sewage would get washed out to sea. One of the biggest of these was at Cross Ness, which is a pumping station in southeast London in Thamesmead. They open it twice a year for visitors, and I had a look in relatively recently. And they have these really quite marvellous steam engines which have been beautifully preserved from Victorian times, which were designed to lift the sewage 30 meters and then discharge it on the ebb tide. Of course, this was only a temporary solution, but it's quite nice to see the Victorians attempting a major fix to this problem. I had the opportunity to go inside some of the old Victorian sewers. This is an old sewer constructed by Joseph Basil Jett in Pimlico. They're not really fit for purpose nowadays. You can see that's me a long time ago in this big sewer. And the fact that Victorian engineering isn't fit for purpose has created lots of problems in central London. You can see there are, this is one of the old Victorian water mains, which is in the process of being replaced by a plastic water main. But there are various difficulties with doing this, which give rise to various leaks, tube stations being flooded, and other engineering issues. So if you consider what's happened to the groundwater in central London over the past, 160 years, you can see that because of quite overzealous abstraction, the mean groundwater level has plummeted from Victorian times to about the 50s or the 60s. So initially, the groundwater level was in the London clay, and then it went down, 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 right into the chalk in the 60s, where it stabilised due to various water abstraction acts which were passed by the Harold Wilson Labour government in the 60s. Following which, the groundwater level in London has slowly crept upwards until about 2000, 2005, after which it's maintained sort of broad stability. So the upping and downing of the groundwater level in central London has posed various engineering points of view. You see, when the water level goes down, you get subsidence. When it comes up, you get uplift. And these are both quite bad for tube tunnels, amongst other things. They pose deleterious consequences for the lateral positioning of tube tunnels. So since about 2000, groundwater level has been about roughly stable, which is ideal from an engineering point of view. These are the fountains at Falcon Square. Originally they were artesian, so the water came up out of its own steam, of its own pressure, but now they're powered by, or rather they're connected to the mains, to mains water. This is a figure from a few years ago, which shows the supply-demand deficit for the London region. So the light blue line up here is how much water is demanded by the southeast. The dark blue line is the supply, effectively. And you can see that there is a yawning gap between supply and demand. Now, there have been various different ways that have been suggested in order to address this huge gap between supply and demand. None of them really fit the current mold of low carbon environmental sustainability, which we hear so often these days. So what Thames Water are doing mostly these days is they are taking water from the River Thames and they're removing the salt from it. So this is a desalination plant which opened 11 years ago in Barking in East London, which effectively renders Thames water suitable for drinking. This is fine, but it uses huge amounts of energy, huge amounts, because it's an electrical process and one needs to charge the electrodes in order to get rid of the various nasties from the River Thames. So, motivated by the fact that there's no real solution to London's supply-demand deficit, a few years ago I undertook some research which was mostly concerned with the chalk aquifer. So the idea of using the chalk as a kind of natural filter had actually been mooted nearly 100 years ago. This is an article from the Standard in the 20s, which speaks of the chalk being some form of a system that was able to transform dirty water into a soft water suitable for man and beast. Very nice prose there. And indeed, this idea has been taken up recently by journalists. This is an article from The Guardian 11 years ago, which refers to another scheme somewhere else in the world, where they use rocks in order to scrub the various nasties from grey water in order to produce a new type of fresh water. So I was interested in using the chalk for this end, so we did some modelling. We looked at an outcrop. This is an outcrop in Kent, near Ramsgate, and we wanted to simulate what would happen if you pump water from the left-hand side of this outcrop to the right-hand side of the outcrop in purely theoretical conditions. And this is the photo you saw earlier. So for this modelling process, first of all, one has to digitize the fractures, because the way in which water flows through the chalk, it mostly flows through fractures rather than the matrix itself. So the fractures were first digitized, and then a mesh was generated, and then we did some modelling. So what this model is showing is if we simulate what happens if we pump water from this chalk outcrop. All of these little filigree lines are fractures, which we traced from this outcrop here. What would happen if we simulated pumping water from the left-hand side to the right-hand side? And the blue colour here is the water that I'm simulating pumping in from the left-hand side. So initially you can see that the water, it just follows the fractures, as you can imagine. I mean, the fractures that have an aperture, water is going to preferentially flow along there as opposed to through the matrix. After quite a long time, maybe 3 or 4 weeks, this is what happens. So you can see in my model domain, the water that I've pumped from the left-hand side under pressure to the right-hand side has reached the right-hand side. But we've also got a lot of diffusion, which you can see from these kind of diffuse blue areas here. And if the theory was that we wanted to remove various nasties like viruses, pathogens from grey water by pumping it through chalk, where the water interacts with the chalk matrix in these blue areas here is really where it happens, because this is where the water is going into the matrix, it's being forced under pressure into the matrix, it's absorbing onto the chalk, the water is continuing, but the various viruses, nasties, whatever, within the grey water, they're staying within the matrix. So what results out here on the right hand side is clean water. And you can see this process happens after what is that, about 7 weeks, maybe 46 days, 47 days. This was just one point of my talk, and I don't want to go into it in a huge amount of detail, so I'd be happy to answer questions about it afterwards. In order to accompany this modelling, I also took some cores, some boreholes from this particular outcrop here in Kent. And what we did was, in the laboratory, we simulated what would happen if you forced grey water through the chalk under a pressure gradient. So this is a laboratory setup which essentially shows the chalk core here in a holder, pressure gradient across it, and we're forcing some form of effluent across it to see what happens. When I say effluent, I mean kind of grey water, shower water, just to see how effective the chalk is as a natural filter in removing various things in the grey water you don't want to be there. So this is a graph which shows concentration of each of these elements on the y-axis, and the x-axis shows time. So first of all, what I'm showing is elements that were already there within the chalk core. So sodium, magnesium, sulfur and iron are all related to seawater. So when I plucked this chalk core out of the cliff, it was wet. These were all already there. So what you can see, I'm flushing the chalk core through with some form of grey water under pressure, and the existing water that's in the chalk core, the seawater, is getting flushed out, which is what you might expect. So after about 40 minutes of subjecting the chalk core to a pressure-filled water test, all of the seawater goes away. That's fine, not particularly remarkable. What is interesting, however, is if you look at elements that were within the stuff that I was putting through the chalk core, various nasty elements like molybdenum, nickel, arsenic and cobalt, which you might expect to be present within sewage. So what you can see is that after a certain amount of time, not all of the elements are fully recovered, particularly not arsenic, particularly not nickel and cobalt. So what's happening is these elements are getting absorbed onto the chalk matrix, which means they're being taken out of the water, which is what we want. So this really gave us a lot of confidence that if sewage or kind of treated sewage or grey water were to be forced through the chalk aquifer under extremely controlled conditions, chalk could act as a natural filter that would remove things like these elements, molybdenum, nickel, arsenic, cobalt, which would stick to the rock, which could later be removed and taken somewhere else. So this gave us a lot of succor, a lot of support that the rock could be used as kind of a natural scrubbing element, like a natural disinfectant. And Thames Water are extremely interested in this, and we're working with them to develop trial schemes in North London. Okay, nearly at the end. One final slide. I did mention at the beginning something about cooling down the London Underground. And I thought it'd be nice just to mention to you all some research which is going to take place at Holloway next year. So I actually got funding for this project about 4 days ago. So this is super new. This is extremely new research, and this is conducted in tandem with Transport for London. So if you think about travelling on the London Underground in summer, it's very hot, it's quite unpleasant. You think of people who may have health conditions, suffering unduly or fainting, and there has to be something done about this. I mean, it's not just a public health problem, it's also an engineering problem, because the rails expand, the tunnels expand, and trains don't run on time, which Transport for London basically doesn't want. So some of the newer rolling stock is air conditioned, which is great. If you've been on the Circle Line recently, it's fairly cool in summer. But the stations, there's no solution to the extremely hot summers in the stations beyond the kind of fans which you may have seen, which shifts hot air around. So our contention is that buried river water, we saw the buried rivers earlier, and also groundwater, which is pumped from the chalk, could usefully be employed as a way to cool down stations on the London Underground network in a sustainable and low carbon manner. So I've got no more exciting figures than this to show you, because essentially my PhD students and I, we've done nothing yet. But the idea is the cold water, water from groundwater is fairly constant, about 12-14 degrees Celsius, would be passed through a heat exchanger or a heat pump. You might have heard of ground source heat pumps, through which hot air would be passed from the tube station, and then there'd be an exchange of heat to render the stations maybe about 8 or 10 degrees cooler. The question is what to do with the hot water after it comes out of the heat pump, whether to put it back in the river or the aquifer, or whether to put it in the sewer. We don't know yet. So this is something which is going to take a lot of research time over the past 2 years. So hopefully, you know, within 2 years, maybe in 2023, 2024, we should begin to see some working prototypes in a couple of stations across the London Underground network, because this is going to become an increasingly severe problem, especially as the effects of climate change begin to accelerate. Okay, so I don't really have much more to say on that, because I've done I've done very little research on that. Those are my contact details. All of these papers I have, all of the figures I've shown are from various parts of these papers which I've published over the past 10 years. So please feel free to look them up if you are interested. Okay, 25 past 8. Thank you very much.